Okay, we're going to continue on here. We got into the nuclear chemistry chapter, which I think is 21. And we talked about sort of types of radioactive decay. Remember, there's certain sort of particles. There are alpha particles, which are 4-2. Or again, you can use the helium symbol for that. There's also beta particles, which uses the beta symbol, or you can use the E for like an electron for that. We also have our gamma. We also have sometimes a proton being given off or involved. We also have a neutron, a positron, which again uses the same sort of symbols there as our beta particle. Um, so remember that when we do have some type of decay through emission or something like that, that particle will typically be there on our product side. If it's some type of bombardment or electron capture, or you're bombarding, that particle is going to be on the reactant side. Because, as we talked about, nuclear reactions involve pretty much changing everything within the nucleus. Um, we do not get sort of the conservation of elements like we do in a normal chemical reaction, where pretty much it's only electrons involved in terms of making and breaking those bonds. So the way we balance nuclear equations is a little bit different. We do balance them through really making sure that when it's all said and done, if you add up all the total mass numbers on the left-hand side of the arrow, they should equal all the mass numbers on the right-hand side of the arrow. And in terms of atomic numbers, on the left-hand side, they should also equal the atomic numbers there on the right-hand side. Remember, it's the atomic number, which is our number of protons, which will tell us, sort of what will be sort of formed as a result of this decay or if something's missing. So that's usually, as we did there in those examples, where you want to start with, kind of figure out the atomic number, go to the periodic table, and figure out what element it may be. And then you obviously can figure out the mass number. Now, remember, in certain cases, the mass number doesn't change, but it does change. And that's because, again, in certain cases, we are converted, say, a proton into a neutron. So although the protons go down, the neutrons go up, but that sort of balances out the mass number to still stay the same. And again, that's why it doesn't really sort of change. And we do typically get these particles as a result of, converting, say, protons into neutrons, neutrons into protons. We also talked about stability, and one of the major things that you could look at in terms of stability is the N to Z ratio, which is basically your neutrons to proton ratio. And there is sort of a belt of stability or a valley of stability where, depending on sort of the atomic number, like 1 through 20 is a good ratio of 1, 20 to 40 is like 1.25, and so forth. You could calculate the N to Z ratio for a particular isotope, and you could determine whether or not it's going to be stable. If it's not stable, it will usually find itself either above or sort of below this valley of stability, belt of stability. And if it's above, it will kind of come down to it through sort of a beta decay. If it's below, it will then kind of come up here through electron capture or a positron emission. As we saw, they both will essentially give you the same product, regardless of which ones you do. As we also saw, it doesn't necessarily mean that you'll get a nice perfect ratio, after it does that sort of decay process, but it should move it towards the sort of belt of stability in sort of the correct direction. Any questions on any of that stuff there? Uh, So this is, I think, where we left off. So let's talk a little bit about decay series. And in a decay series, what we essentially have is a parent nuclei that will continue to basically go through a decay process and sort of decay reactions, emitting off particles until it pretty much hits something that is stable. So it will continue to sort of go one right after the other and continue this sort of decay process until it hits that sort of stable nuclei, and that's what's referred to as a decay series. Now, there's a couple of different ways that you could sort of, for example, approach figuring out what's happening in decay series. You can do what we did previously, which is just simply write the reactions for every sort of decay process that occurs. In this case, because it is a series, what happens is your product of the first decay will become your reactant of the second one, and then your product of the next one will become the reactant of the next one, and so forth. So that's a way you can do it. Just balance it up, use periodic table, and do that as well. Now, if you are just maybe interested in where you may end up, and pretty much all you got going on are alpha and beta decays, you can just kind of do it mathematically and figure it out. For every alpha decay, you can basically subtract 4 from the mass number up on top and 2 from the atomic number that's on the bottom. And for every beta decay, you basically could just add 1 back to the atomic number on the bottom. So if you're just sort of interested in the end, that's the way you can do it. So just to kind of show you maybe how this goes here. So let's just say we had uranium 238, and that is number 92 up there. All right. And let's just say this went through an alpha. We'll just do a short series here. It will not hit something stable at this point, but just to show you sort of how this process works. Let's just say it went through an alpha, beta, beta, alpha sort of decay series, or start of this decay series. So if you're going to do it sort of like we did with our equations, what you would do is just go with your 238 uranium to start with. It would go through the first decay process, which is the alpha. And again, you can use the helium or the alpha symbol for this. This would give you a missing atomic number of 90, right, to balance it out to 92. If we go to periodic table, that is TH. Up on top, that's going to take us to 234 in this case. Now that 234.90 will then go through the next decay process, which is our beta, and a little 0 minus 1 happening there. Here we do need to go up because that's -1, so we would go to 91. We would also go to the periodic table there and look at 91. That's a PA. Up there in terms of the mass number, it would stay at 234. Then the next step would be the guy that we just created there would go through the next decay process, which is our beta. Again, we got to step up 1 there to counter out the -1. That's going to take us to 92, which takes us back to uranium at 234. And lastly, here we would go 234.92, and it will go through our last decay process here in our very short little guy here just to demonstrate how we could get to everybody. We would have our alpha particle here. That's going to take us to 90, which takes us to TH. And up on top, we would have a 230. So you could just do individual sort of nuclear equations and balance them out. And again, sort of your product of the first one becomes your reactant of the second one. Again, if we were just interested in maybe what we get at the end of this journey, and maybe we're not interested all the way through here, we would see that we have 1 and 2 alpha, which means from the top we should subtract 4 twice, and from the bottom we should subtract 2 twice. We also have 2 beta particles, which means on the bottom here we should add 1. So if we just did the math here, that's going to be basically 238 minus 8 gives us 230. That's going to give us 92 minus 4 plus 2. So that's going to take us down to 88 plus 2 is 90. And there is our sort of end product there of our decay, short decay series here. So if you're just interested at the end and they're just alpha and betas, you can kind of do it mathematically and sort of figure out what you'll get at the end, or you could do a step by step there if you're interested in what you will produce step by step. That's probably the better way of doing it. If you have a question where it asks what is sort of the product after each of the steps, then clearly probably this is the best way to do that. But you can still do it mathematically after each step too if it's alpha and beta as well. Any questions on that there? Again, obviously, in a true decay series, it would continue this process, as I said, until something sort of stable gets hit. So looking at uranium-238, we just did the first little bit of it here through here. But you can actually see in this case, it actually will branch off into a couple of different directions, but they will both pretty much end up over there at our stable lead. That's on the bottom there, lead 206. But it can go through two different routes to sort of do that. And again, that's very common in sort of nuclear reactions because there's a lot of interchange of what's happening in the nucleus. There are different pathways. You don't necessarily always get sort of the same thing that comes off. Any questions on that there? All right, then let's talk about kinetics and radioactive decay, which, should hopefully be reviewed for us because we talked about kinetics in this class, so that's good. But all radioactive decay follows first order kinetics. So if you remember our first order sort of rate laws, we basically use the exact same ones here for radioactive decay. So just a reminder, that is then like the natural log of A is equal to the natural log of A naught minus KT. And we also have our half-life, which is used a lot here, and that is the natural log of 2 divided by K. Now, I will say, because it's nuclear chemistry, they sometimes like to use different symbols for things. So as you can see down here, a lot of times they'll use N for nuclide instead of sort of concentration, but it's basically the same thing. Also, sometimes they will use lambda here for K. And in the sort of application of nuclear chemistry here, K or lambda is actually what is referred to as the decay constant instead of the rate constant. So that is what is referred to as the decay constant. Nuclides, T is still time, just like it is in our first order. And remember that sort of our decay constant here will have similar units, but also remember that it doesn't have to be seconds, but it is some unit of time, and reciprocal time, 1 over some unit of time. Now, one of the sort of major differences between sort of how we use these equations in sort of our kinetics situation versus how you use it here in this sort of radioactive nuclear situation is in terms of what we could put into this sort of spot here. And usually what we did in sort of the kinetics chapter is we use concentrations in there. And you could still use concentrations, but you could actually use any unit of sort of concentration that you want. So it doesn't necessarily have to even be a concentration. So those could be like grams and grams on both sides. They could be milligrams and milligrams on both sides. They could also be, which is also very common, is a unit of radioactive decay or a rate of decay. So some type of rate of radioactive decay, like counts per minute or something like that. So it could be some type of rate that's used in there. Also very common is percentages. So like, 50% of it's still left or 20% of it's still left. So you could use like 100% for initial, 20% for what's left, or you could do like 1 and 0.2. So those are other type of situations you could do it. So you definitely can use any type of unit in here as long as, again, they are the same unit, so everything cancels out correctly. I will say probably more than what we did in the kinetics chapter is we will oftentimes use both of these equations together. And the reason for that is a lot of times in this type of problems, they'll give you the half-life, and you will use the half-life equation to get the decay constant and then use that decay constant in the next equation. So very, very common. We use both of these equations together. And like I said, they kind of give you the half-life versus the decay constant. You have to sort of figure it out. Remember, our graph is still the same here. Natural log versus time yields us a straight line where the slope is equal to negative of the decay constant in this particular case. And this is what we expect to see happen. We should see a decay over time of what we started with. So half-life obviously is the time it takes for half of whatever you started with to go away. So after the first half-life, you started with 10, you got 5. After the second one, you got 2.5. After that, I need a calculator, but you keep dividing by 2. But in terms of half-lives, they do range from very, very quickly, like we can see on the bottom here. That's like super quick, to super, super long, like we see here. That's like 1.4 times 10 to the 10 years for half of whatever it is. Also, some different sort of emitters there. So uranium 238, carbon 14, 5730 years. So why don't we try one here? If you have a 1.35 milligram sample of plutonium 236, how much of it will still be there after 5 years? The half-life of Pu 236 is 2.86 years. So why don't you take a moment there and calculate it again using hopefully your remembered kinetics equations. Yes. Okay, so let's take a look. So since you sort of see this, we know it's going to be our first order, and really you can still roll with the same sort of formulas without the other symbols. So you can just use the regular kinetic symbols if you like. And we have our half-life here of natural log of 2 over K. In this particular case, we do have the initial sort of concentration of 1.35 milligrams. We want to know how much is going to remain. And we do have the time that is 5 years. So if we look at our sort of equation, we're looking for this guy, we have this guy, we have this guy. But as I mentioned before, very common in these type of problems, you are missing the decay constant. And again, that is where obviously our half-life information comes into play. So we're going to use our half-life equation here to solve for the decay constant, which would be the natural log of 2 divided by the half-life. They basically switch places. These two guys basically multiply and divide. And that will give us the natural log of 2, which is that 0.693 number you sometimes see, 2.86 years. And that's going to give me here a natural log of 2 divided by 2.86. Give me a 0.24236 reciprocal years. And again, 1 over a unit of time is what we expect for first order. Now we do have our decay constant and we're good to go. Also, one thing that you should make sure of as well is unit-wise between T and your decay constant. You want to make sure that the time part of it is in the same unit. So that's also very commonly sort of different. In this case, we're good because they're both in years. So we're going to go natural log of A equals natural log of 1.35 minus 0.24236 times 5 years. All right, so cleaning up the right-hand side there, it's going to give us here the natural log of 1.35 minus 0.242359154 times 5. Going to give us the natural log of A is equal to negative 0.91169, I believe. We're going to E both sides, right, to get rid of that. So we're going to E this here. And that will give us an A of 0.402. The units here will be milligrams, just like the original one that we had there. Any questions on that there? Make sure here. This does make sense as it has obviously gone down, which is what we would expect here, right, with radioactive decay. So again, if you end up with a higher starting amount, you are definitely going in the wrong direction. So that should always be sort of less than what we started with. Any questions on that one? Good news is it's really just a regular kinetics type problem like we did at the very beginning of the semester. All right, so why don't you try one here? Radon 222 is a gas suspected of causing lung cancer. It's produced by uranium decay. Assuming that we have no loss from leakage, if there is 10.24 grams a radon 222 in the house today, how much will be there in 5.4 weeks? Half-life is 3.8 days. Okay, so let's take a look at this one. Kind of same idea. We're going to go with our sort of formulas here. And again, let's see what we got here. We got an initial 10.24 grams. We want to know how much will be in there after 5.4 weeks. And again, we are missing the decay constant, so we do have the half-life here of 3.8 days. Now, just looking at our units of time here, we do have one in days and one in weeks. So we do need to do a conversion. It doesn't really matter sort of which one you convert, but you do need to get them into the same units. So I'm going to leave my half-life in days. I'll eventually convert my weeks into days for my time. So if I can solve for my decay constant, natural log of 2 over the half-life, which once again, I'm going to leave in days here. So if you converted the half-life into weeks, you will have a different number that I have right here at this point. Got something like 0.1824, again, reciprocal days. We'll convert that weeks into days. So 1 week, 7 days, I think they say. So 5.4 times 7 gives us 37.8 days. So now I got my unit of time, basically both in the same unit. Now we could go into here, natural log of A equals natural log of 10.24 minus 0.1824 days, and my time also in days. Now, obviously, again, if you did weeks, you'll have some slightly different numbers here, but in the end, it should come out the same. We got the natural log of 10.24 minus 0.1824 times 37.8. Going to give us the natural log of A is equal to negative 4.56868876. Going to E both sides there. And when we do that, that will give us a final concentration here, or amount, I guess, of 0.0104. And these would be grams as well. Any questions on that one there? So once again, pretty much it's a basic kinetics type problem. And as you can see, you could use really any type of unit for the concentration part of it. All right, here. Now, in addition to sort of problems like we did there a second ago, we could also use radioactive decay to do some radioactive sort of dating. We could use radiocarbon dating, where we look at carbon-14 and use the carbon-14 half-life and look at, how much carbon-14 there is left. We also could use uranium 238 dating. You can also look at how much lead is produced and the difference between lead and what you started with. Can also help you determine how old something is. It is still the kinetics sort of equations, except in this case, you're solving for time to figure out how old something is. So let's take a look at this one here. An ancient skull gives 4.5, and this is actually a rate of radioactive decay, and that is disintegrations per minute. And that is actually per gram of carbon here. So it's actually per gram of carbon. It's not Celsius or anything like that. And that's important because that's going to tell us that we actually want to use the half-life for carbon, as we see here, 5730. So we would use the 5730 years as the half-life here of carbon. So an ancient skull gives 4.5 disintegrations per minute per gram of carbon. If a living one gives 15.3 disintegrations per minute per gram of carbon, how old is this skull? So essentially here we'll still use our kinetics formulas here from our first order. And in this case, we actually have the rate here of an ancient one, which is the ending part there. So 4.5 disintegrations per minute per gram of carbon. Our living is sort of where we start. So that is 15.3. And we're looking for how old something is. So in this case, we have this guy, this guy, and this guy. Once again, like the previous problems, we are missing the decay constant. And again, that's where the per gram of carbon comes into play. So we use carbon 14's half-life here. So we'll use the half-life equation like we did previously there to get our decay constant. And in this case, that will give us the natural log of 2 divided by 5730 years. And that will get us 0.000121 reciprocal years. Now I have everything I need. I can go into my equation. This will give me my natural log of 4.5, which is our kind of ending natural log of where we started, 15.3, minus our decay constant here. And here we're solving for time. Our unit of time, when it's all said and done, will be years here in this particular case, based off of the decay constant. So again, just like we did sort of in kinetics, I'm going to take the natural log of 4.5. I'm then going to subtract the natural log of 15.3. And that's going to give me, so I'm basically going to subtract this guy here to the other side. And that will give me minus 1.223775 equals negative 0.000121 reciprocal years times t. We're then going to divide this to the other side, including the negative. And that will give us a time of like 10,114 years. And since everything looks like three significant figures, so maybe like 10,100 years, something in that ballpark. So it's pretty old, about 10,000 years old. Still, as you can see, really still just first order kinetics type problem, just solving for time really in this case. Any questions on that one there? So as you can see here, rates of radioactive decay can be put into the kinetics equation. And again, your final one should obviously be the lower rate, and your initial should always be sort of the higher rate. All right, so why don't you try one then here? All right, so they dated a civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon for a rice of grain that was found on the site? So see what you come up with. It is carbon, so perhaps the same half-life. Yeah. Okay, so looking at this, once again, we are going to use our equations here for first order. And in this case, we are given time of 15,600 years. A living sample, so living would be initial, or 20 counts per minute, again per gram of carbon. Means that we are going to use our same half-life that we had there, which was our 57. Basically, where is that? There it is, 5730. And in this case, we're looking for how many counts per minute will it give at the end. So that is basically what we're looking for. And again, here we're going to find our decay constant, which is the same number that we used on the previous example, since they're both carbon. So again, putting that into our formula there will give us our same decay constant in this case of are 0.000121 years. So put it in there, natural log of A equals natural log of our initial, which is 20, minus our decay constant. And here our time is 15,600 years. Once again, we got years there and years there, so we're okay in terms of units. You always want to make sure, again, that those both are the same units, so everything works out correctly. So if we do the right-hand side here, we will end up with, looks like maybe a natural log of A is equal to 1.108132227. Again, we're going to E both sides there. And that is going to give us basically here 3.03. The units here will be the same units as our original rate, which would be counts per minute per gram of carbon, basically. It obviously is less than what we started with, which again is what we would expect as it is much older. So it's already gone through a lot of decay, so it's not going to be giving off as much sort of radiation, if you will. Any questions on those there? So the good news is, like I said, pretty much the same thing we did there in the very first chapter, first order kinetics. Basically, those are two equations. You can still use it the same way as you did before. Kind of the only variation of we could kind of put really anything in terms of the concentration. It could be grams, milligrams, like I said, percentages, rates, and all those type of things. Any questions on any of that there? Okay. All right, so let's talk a little bit about fission and where the energy of fission comes from. And a reminder that fission is really the process of a unstable nucleus basically splitting off into two new sort of isotopes. It usually will give off a number of neutrons and lots of energy associated with it. This could be spontaneous, and like I said, something being unstable. You also can sort of shoot a particle at something and sort of cause it to go through this fission reaction. So one way that we can calculate the energy here associated with this is through Einstein's equation of E is equal to mc squared. C is the speed of light, which is our 3 times 10 to the 8 meters per second. M here is actually, in this case, what is referred to as the mass defect. And the mass defect is there is a certain difference in the mass of the actual isotope itself and the mass of really the components of the nucleus that make it up, the protons and neutrons. So that slight difference in mass gets sort of converted via, say, Einstein's equation here into energy that's released as this sort of nucleus is formed. And the result of that is, as we've talked about, it gives off a lot of energy at fission reaction. As you can see here, you get about like times 10 to the 13 joules of energy in a fission reaction versus your really exothermic reaction of a chemical variety, just a chemical equation or reaction of 10 to the 6. So a lot more energy is produced in these fission reactions. Again, because you're pretty much tackling in the nucleus and changing those particles within the nucleus. So again, that's a big energy sort of impact here. Now, the mass defect, as I mentioned, is really the difference, as I said, between really what makes up the isotope and the mass of the isotope. Most of the time, we are interested in really just the protons and neutrons because they are really the most of the mass of the atom. As you know, electrons are pretty much 1,800 times or so less massive than protons and neutrons. So most of the time when we do these sort of calculations, we're interested in just the protons and neutrons. Sometimes people will also include the electrons in the calculation, but for here, we're just going to focus in on the protons and the neutrons because we're pretty much most of the mass of the atom anyways. So the energy that's released when the nucleus is formed is what is referred to as the binding energy. And there are a couple of ways that you can approach these type of problems And I'll show you both, and you can choose which way you want to do it. You can use Einstein's equation equals mc squared. You could also use a couple conversion factors that are really based on Einstein's equation that can kind of get you there as well. 1 mega volt is equal to 1.602 times 10 to the minus 13 joules. It's not negative or anything, so that's just from PowerPoint. And 1 AMU, a mass defect, is equal to 931.5 mega volts. Now, when we look at binding energy per nucleon, and nucleon is basically the number of protons and neutrons that are in the nucleus, basically like the mass number. That is a measure of stability. So that is another kind of very common measure of stability. And two common sort of units are used when you calculate binding energy per nucleon. Joules per nucleon is a very common unit, and are mega electron volts per nucleon. So these are two sort of units of binding energy that are used. And that is really what this first conversion is for. It will take you from, say, mega electron volts to joules and back and forth and stuff like that. So the measure of stability here with binding energy is the greater the binding energy per nucleon, the more stable the nucleus is. So you could use binding energy per nucleon and compare different isotopes. And again, the one with the higher one should be more stable. So for example, here, if we were looking at fluorine 19 and we wanted to calculate the binding energy per nucleon, and this was the atomic mass of that isotope there, 18.9984. The first thing that we would want to do is calculate what is referred to as the mass defect, and that again is the difference between the protons and neutrons and the mass of the isotope. So in this case, we know the number of protons here are 9, as that's the atomic number. We know the number of neutrons here is 19 minus 9, which is our mass number, minus our atomic number, which is 10. So we could calculate the mass defect by taking 9 times the mass of a proton, which is this number right here, 1.007825 AMU. And we could add it to 10 times the mass of a neutron, which is right there, 1.008665. And then we're going to subtract it from the atomic mass of this isotope, which is 18.9984 AMU. And if we do that there, we will end up with basically 0.1587, we'll call it, AMU. This is the mass defect. That is, again, is sort of the difference in the mass of the components of the nucleus and the mass of it by itself, the isotopes. So that's what's going to get converted into sort of energy. So if you wanted to, at this point, there are two options to sort of get you there. We can use Einstein's equation here of E is equal to mc squared. Again, the m here is going to be our mass defect. So putting that in there will give us 0.1587 AMU times our 3.0 times 10 to the 8 meters per second squared. That's going to give us there 1.428 times 10 to the 16. The units here are AMU, meter squared, second squared. So that's not really the units that is useful for us. So we could do this conversion here, 1.428 times 10 to the 16 AMU meter squared second squared. And we could actually divide this by our friend 6.022 times 10 to the 26, actually, not 23, but 26. AMU, and that is because 23 is grams, 26 is kilograms. So instead of 23, 26 to go to kilograms, that will get us here. 2.37 times 10 to the minus 11 kilograms, meter squared, second squared. And you hopefully should recognize that is the same thing as a joule. So a kilogram meter squared second squared is equal to 1 joule. And that means that we would then have 2.37 times 10 to the minus 11 joules. We could then divide it by our nucleons, which in this case is our protons and neutrons, our mass number of 19. And we will end up with something like 1.25 times 10 to the minus 12 joules per nucleon. Any questions on that calculation? Now, if we wanted mega electron volts per nucleon, we could use that conversion that we saw on the previous slide, which is 1.602 times 10 to the minus 13 joules is a mega electron volt. So we'll take that divided by 1.602 to the minus 13. That gives us something like 7.79 mega electron volts per nucleon, which is sort of, again, the other sort of unit that is commonly used. First off, any questions on that calculation? Now, as I mentioned before, if you do not want to use sort of that Einstein's equation, you can just use those conversions that we did before or saw on the previous page. You could pick up with this guy right here and go, there are 0.1587 AMU. And if we take that number there, and we can do the 1 AMU is 931.5 mega electron volts, which is that conversion. Going to give us about 147.806 mega electron volts divided by 19 nucleons. Gets us about 7.78, a little different with rounding, but pretty close to what we had. Obviously above, we obviously could at that point also use the same conversion factor going in the other direction there, 1.02 times 10 to the minus 13 joules per mega electron volt. And that should take us back to there as well. So again, you could use those kind of conversions and not use Einstein's equation there, and it will get you basically the same sort of path there. Any question on any of those there? All right, so let's take a look at, again, the binding energy per nucleon. Again, it is a measure of stability. The higher you have, the more stable something is. So we'll kind of roll through that one, which we just did. And here you can see a graph of that. And really at the top of the graph is iron 56. It has really the sort of highest binding energy per nucleon and is really sort of the most stable guy that you could have. Again, what will happen in a lot of cases, as you can see from this picture, is things will either go through fission or fusion to try to get itself close to that stability in terms of nuclear binding energy per nucleon. So why don't you try this one? Calculate the mass defect and nuclear binding energy and mega electron volts per nucleon. Well, we also do joules per nucleon. Let's do them both. For this carbon-16 isotope, and there are some masses of neutrons and protons. Carbon's number 8 on the periodic table. Yeah, so let's take a look. All right, so I got 6 here for carbon. So that means it does have, in terms of protons, 6, which is the atomic number. That means number of neutrons would be 16 minus 6, which would be 10. So we can calculate our mass defect by taking our number of protons there, which is 6, times it by the atomic mass of a proton. We'll use the number that's on the slide. Why not? And we're going to add it to 10 times our atomic mass there for our neutron. We then will subtract it from 16.014701, which is the atomic mass of our isotope. And that's going to get us there 6.1007883. 10 times 1.00866 minus 16.014701. Going to give us a mass defect of 0.1189. Since we're looking for mega electron volts, we might as well just roll in with the formula there, or the conversion factor there that will get us there. That's 931.5 mega electron volts per AMU. We'll take that 931.5. Will give us 110.74 mega electron volts, which we can divide by our nucleons, which is basically our atomic number in this case, which is 16. That's going to give us something like 6.92, I'll call it 1 mega electron volts per nucleon. We also could use the conversion there to get us to joules, which I'll just kind of do to the side here. 1.602 times 10 to the minus 13 joules per mega electron volt. And if we do that there, looks like 1.11 times 10 to the minus 12 joules per nucleon. Any question on that one there? Obviously, again, you could also use the equals MC squared, putting our mass defect in there, our speed of light, and then dividing by Avogadro's number there to 26 will get you the joules, and then divided by the nucleon will get you there. And then you can do the conversion the other way as well. All right, let's take a look at another one here. Iron 56 is 55.93494. Calculate the binding energy per nucleon. And iron, I'll try to do better this time, 26 there. Okay, so looking at this, we've got our protons here at 26, our neutrons, our mass number 56, minus 26, which would be 30. That's going to allow us to calculate our mass defect here. Again, that mass is going to be kind of converted. We'll do 26 times 1.00783 for our protons, plus 30 there, times 1.00866 for our neutrons. We'll subtract that from the atomic mass here of the isotope, 55.93494 AMU. And that's going to get us here 26 times 1.00783. Maybe get my calculator to work. Maybe it gives us a number. There we go. Times 30 times 1.00866 minus 55.93494. Looks like 0.5284 AMU. Again, depending on which way you want to go, if you want to use the Einstein equation, it will look something like this. Since I did it the other way on the previous one, I'll do it this way here. Putting that in there will get us 4.756 times 10 to the 16. AMU meters squared seconds squared. Here again, we got to divide by Avogadro's number to the 26 to get it really into joules here. And if we do that there, we'll end up with something like 7.898 times 10 to the minus 11 joules. We can then divide it by our mass number, our nucleons, which is 56. And that'll get us something like 1.41 times 10 to the minus 12 joules per nucleon. We then can convert it at this point if we wanted the other number there. By taking 1.602 times 10 to the minus 13 joules per mega electron volt. And we'll end up with like 8.803 mega electron volts per nucleon. Again, didn't really specify which one, so we go either way really in this case. Any questions on how to calculate binding energy per nucleon? Now, if we compare our binding energy per nucleon for our isotopes here, we could see that iron 56 had 8.8 mega electron volts. Our carbon 16 has 6.92, and I think we did ended up with 7.78. So out of those three, we can see that the iron 56, which was on the top of that graph, had 8.8 mega electron volts per nucleon, which is much higher than our fluorine there, and also higher than our carbon 16. So it'd be kind of iron, our fluorine, and then our carbon 16 if you're comparing stability based on binding energy per nucleon. Any questions on that there? All right, we will lay it up there for today.